question number 3. A gasoline engine takes in so much heat, so Q in is 16,100 joules, and delivers a work of 3,700 joules per cycle. The heat is obtained by combustion gasoline with a heat combustion of, so heat of in is 4.6 times 10 to the 4 joules per kilogram. Okay, sorry, joules per gram. So they say, what is the thermal efficiency? Well, the thermal efficiency, we are assuming it's 1 gram per cycle is used. So if it's 1 gram used, then the heat going in is this divided by that many grams. But since we already know the work done is 3,700 and the heat in is 161,000, so if you divide by 2, then the efficiency is simply 37 over 161, 22.9 or 23.0%. Part A. Part B is how much heat is discarded in each cycle. The heat discarded is simply the heat going in minus the work done. Heat going in is 16100 joules minus the work done is 3700. Then heat discarded is 16100 minus 3700. We get 12400 joules. That's heat discarded. Part B. What mass of fuel is burned in each cycle? So Q in we know is 16100 joules. But if you are burning at the rate of that many, so you divide by 4.60 times 10 to the 4 joules per gram, then you're going to end up with grams. So you get 16100 divided by 4.6 to the 4th. You get 0.35 grams per cycle. So that will be part C. And part D, if the engine goes 60 cycles per second, what is the power output in kilowatts? Well, so in 1 second, there's 60 cycles. And we know that each cycle takes up that many grams. So therefore, or each cycle, power output, so that is work done, workout. The workout we know is 3,700 per cycle. And times 60 cycles, that means per minute. Then we can, sorry, per second. This is per second. Then in each second, we get 3,700 times 60. We get 222,000 joules per second. Now, isn't that what we call watts? Or we can say 220 kilowatts. Okay? Now, so that would be the power outage in kilowatts. And what about in horsepower? So you just have to convert 227 kilowatts to horsepower. The horsepower is, now let me see, how many horsepower per 1 kilowatt? Well, 1 kilowatt is the same as 1.34 102 horsepower per 1 kilowatt. So if you now multiply by 1.34102, so I get 297.7 horsepower or 298 horsepower. So that's number 3. And let's see, check the answer. For chapter 18, 6,500, 34%. Oh, that's 34%, that's good. 23%, 23%. 12,400, 12,400, that's correct. And 0.35 grams. 0.35 grams, correct. And 222 kilowatts, correct. Turns to 298 horsepower, correct. So number 5. Number 5 says a certain nuclear power plant has a mechanical power output of 33. So nuclear plant mechanical output is 330 megawatts. Its rate of heat input from the nuclear reactor is, so Qn is 1,300 megawatts. What is the thermal efficiency of the system? Well, thermal efficiency is simply the work output divided by Qn. So since we're talking about megawatts, so I can just use this divided by 1,300. So basically same as 33 divided by 130, which is 25.4%, keeping 3 fixed. At what rate is the heat discarded by the system? Well, heat out is simply heat in minus work done. So heat in is 1,300 megawatt minus 330 megawatts. So basically it's 1,300 minus 330. Again, 970 megawatts. So you could just say 970 megawatts as the final answer. So that's 18.4. Sorry, 18.5. And the answer for 18.5 is 0.25% and 970 megawatts. Okay, let's do number 7. Number 7 says, for an Otto cycle, gamma is 1.40, the compression is 9.50. The temperature of the gasoline air mixture when it enters the cylinder, the temperature of going in at point A of that graph is 22 degrees Celsius plus 273 is 295 Kelvin. What is the temperature at the end of the compression stroke at point B? Now you have to remember, so for Otto cycle you have adiabatic from A to B, that's adiabatic. From C to D is also adiabatic, and whereas from B to C is isochoric, and D to A is also isochoric. Well, let me draw a better graph. So this is adiabatic. It goes up here, goes this, goes right, goes down. Here's my A, B, C, D, and this is the Otto cycle. And this volume and that volume are usually expressed in terms of a ratio. Okay, so they say that temperature here is 295 Kelvin. Now, and then the ratio is 9.5. The temperature of the mixture entering is 22 degrees Celsius. What's the temperature at the end of the compression? So they say, what is TB? Well, because A to B is adiabatic, okay? And then the volume here is R times the volume here. So if I call this one VB, then this should be RVB, okay? Because compression ratio is given here is 9.5 times the compressed volume. So this is actually 9.5 times this volume. Anyways, I know the temperature. If I do this, I should be able to at least figure out the temperature here, because in any adiabatic compression or expansion, you either figure out temperature first or you figure out the pressure first. So in this case, I know the temperature at TA, so I can figure out the temperature at TB by using the formula of TB to the gamma minus 1 at A is same as TB VB to gamma minus 1 at B. So these two ends of the adiabatic is related to this. Since I know the temperature at A, I can therefore figure out the temperature at B, and that's exactly what they're asking for. So let me put the TB, solve TB by itself by moving this TB to the gamma minus 1 underneath, and then factor out TB over TB all to the same power gamma minus 1. But TA is really RVB. So VA is really RVB. So VA is RVB over VB to the gamma minus 1. So these two cancel. TA is 295 Kelvin. R is 9.5. And gamma is 1.4 minus 1 is 0.4. So I can now figure out what TB is now. So TB is 295 Kelvin times 9.5 raised to the power of 0.4. And that gives me 726 Kelvin. So that's part A of question 7. What's the temperature? The initial pressure of the gasoline mixture is 8.5 times 10 to the 6. So PA is 8.5 times 10 to the 4th Pascal. So PA is now given to you. What is the pressure at the end of the compression stroke? What is the pressure at PB? So what is the pressure at PB? In other words, what is PB? Then you know that for adiabatic compression, you have PA VA to the gamma equals to PB VB to the gamma. And since you want to know PB, so I solve for that, then move this guy to the lower left, like so. So PB is simply PA times VA over VB to the gamma. But VA is just RVB. These cancel. So I can now plug in PA, which is 8.5 times 10 to the 4. R is simply 9.5 to the gamma. Now in this case, gamma is 1.4. So put exactly 1.4 up here. Then I figure out PB is simply 8.5 E4 times 9.5 raised to the power of 1.4. I get a pressure of 198. Let me see. Holy cow. 1.99 times 10 to the 6 Pascal. So 1.99 times 10 to the 6 Pascal is the pressure at B. Okay. So what is the pressure at the end of that? So there you go. Two answers for numbers 18-7 is 453.2 degrees. 453. Oh, they put it in Celsius. So 728 minus 273 is 243 Celsius, same thing. So this is correct. And then you have 199 times 10 to the 6 Pascal, 199 times 10 to the 6 Pascal, correct. So that's how you do number 7. So number 9. Number 9 talks about refrigerator. The refrigerator has the coefficient of performance. Coefficient of performance as 2.10. But coefficient of performance is defined as Q in divided by work to remove the Q in to the outside world for refrigerator. So they're saying that this is 2.1. Okay. And then they say each cycle it absorbs, so Q in is 3.40 times 10 to the 4 joules. So how much mechanical work is done to operate the fridge? Well, then what is W? Well, if Q in is already given to you, just plug it in. So 2.10 equals to 3.40 times 10 to the 4 joules divided by W. So W is simply 3.40 times 10 to the 4th divided by 2.10. So 3.4 divided by 2.1, I get a 1.62 times 10 to the 4 joules. So that is the work done to remove the Q. So then the part B says each cycle how much heat is removed to the high temperature reservoir. So in other words, discarded. So Q out in this case will be W plus Q in. And so in this case will be Q in is 3.40 times 10 to the 4th plus 1.62 times 10 to the 4th. We get a total of 5.02 times 10 to the 4 joules. So that will be part B. And this is part A. And then we have number 11. A window air conditioner unit absorbs that much heat per minute from the room being cool. So that is, they are removing Q in is 9.80 times 10 to the 4 joules of heat from the room and discards to the outside air. So Q out is 1.44 times 10 to the 5th joules. So the refrigerator discards this much heat to the outside world. This is heat that is removed from the room. What is the power consumption of the unit in watts? Well, the W is simply Q out minus Q in. This minus that. So 14.4 minus 9.8. So it's 4.6 times 10 to the 4th joule is the work done. Now, this will be the work done per minute, because everything is given was per minute. So question A is, what is the power consumption of the unit in watts? But since this is per minute, to get into watts or power, you have to change that to per second. So this number divided by 60, you will cancel the minutes and you will have therefore watts. So 4.6 to the 4th divided by 60, 767 watts. So that's number 11A. B is, what is the efficiency rating of the unit? Well, efficiency, what is energy efficiency rating of the unit? Well, for refrigerator, it's really called the performance, coefficient of performance. So coefficient of performance is how much heat removed per unit of work done. So it's 9.8 times 10 to the 4th joules divided by the amount of work put in is 4.6 times 10 to the 4th joules. So coefficient of performance is 2.13. Okay. So it's 2.13, that is performance. So for number 11, 767 watts. Well, I got 2.13, but the answer is 7.27, and that is 7.27. What is energy efficiency rating? Energy efficiency rating, EER, is defined to be H over P. That means H over P, and that is what is the heat removed divided by the power put through. But the energy removed divided by power is basically 3.413 times whatever performance is. Okay, so if I do that times 3.413, so I get 7.27. That is EER. So you just need to multiply by this number, which converts the units of joules that ratio, but instead of using joules by joules and get a pure number, you actually get to convert the Q in terms of BTU, and instead of joules at the bottom, the power became watts. So, you know, it's just British units. I'm not even sure why we bothered to use this. Anyways. So that's why the answer is 7.27. You just have to multiply the K by 3.413, the fixed ratio constant. Okay, so that's number 11. Number 13. Number 13 says for the Carnot cycle engine whose high performance reservoir, whose high temperature reservoir is at 620 Kelvin. Now, if you recall the Carnot cycle, okay, the Carnot cycle has adiabatic this way, but isothermal this way. So this is adiabatic, isothermal, isothermal. So this is your Carnot cycle. This is work done. Okay, so for question 13, it says the high temperature is at, so this temperature, this is isothermal, so this temperature is at 620 Kelvin, and the heat that it takes in, Q, is 550 joules, and it gives up 335, so heat out here, is 335 joules at the low temperature reservoir. Okay, so the question is, how much work is done? So what is the W area here? And what is the temperature at the lower temperature? And what is the efficiency? Okay, so we know that at high temperature here, the temperature given to you is 620. And this is isothermal. So isothermal means that the work done, Q equals the work done. And the work done and the Q is the same, 550 joules. But the work done for isothermal is nRT ln V2 over V1. Okay? And you're told what the temperature is. So temperature is 620. So this is nR 620 Kelvin ln V2 over V1. Okay? So now we can say this is 550, and therefore we should be able to figure out what V2 over V1 is, or at least we know ln V2 over V1 is. Okay? Now, at the bottom here, you have 330, which is nRT lower, which is the lower temperature here, also of ln, in this case, this one over that. If I call this A, B, C, D, so it will be VB over VA, okay? And this will be VD over VC. Okay, but we know that though is that the other two ends are here, these two ends are adiabatic. If they're adiabatic, then the ratio of their volumes and their temperatures are related. For example, because it's adiabatic, we can say that TA VA to the gamma minus 1 is equal to TD VD to the gamma minus 1. See? And we can also say on this end is TB VB to the gamma minus 1 is equal to TC VC to the gamma minus 1. So when you divide these two, like so, you can see that VB over VA, so for example, TA over TD, in this case is VD over VA to the gamma minus 1, and in this case, say TB over TC is VC over VB to the gamma minus 1, okay? But TC and TB, TC is here, is same as TD, right? Because it's isothermal. So this is actually same. And TB and TA are actually the same because it's isothermal. So this is also same. Which means is that VB over VA is really the same as VC over VB. Because these two are identical. So that gives us VB over VA is same as VC over VB. So if you now rearrange all this, that is, if I move this upside down, that is VB over VC is the same as VA over VB then. Okay, if you exchange these two. Which means that, oh, I want the other way around. I want VD over VC is the same as the reciprocal of V and A. We know that ln reciprocal is just negative, right? So this is just negative of VA over VB. But since these two are identical, then when you divide these two, they cancel. And these cancel. Okay? Well, of course, we don't need to change the sign because this would have been negative anyways. So these two cancel, then we can now say TL is simply this times this divided by that. Okay? So because from here we can say TL over 620 is same as 335 over 550, and therefore TL is 335 times 620 divided by 550, and you get 337, so 378 Kelvin. Okay, so the lower temperature will be 378 Kelvin, and that is the first answer. So this is question number 13. 378 Kelvin, exactly. Okay, so number 13, 378 Kelvin. How much mechanical work is performed during each cycle? How much mechanical work is done in this case, since these two are adiabatic, so the work done will simply be Q in minus Q out. That is 550 minus 335. So 115 joules. So that is the work done is 115 joules. Or did I say 115 or 215 joules? 215 joules, so that's correct. 215 joules is the work left in here. And then the lower temperature is indeed 378. And they now want to know what is the efficiency. Well, efficiency is simply amount of heat going in divided by work. The amount of heat going in was 550. So 550 divided by the work, 215. Oh, sorry, the other way around. 215 work divided by Q in, which is 550. So 215 divided by 550. I get 39%. So 39% being the efficiency of this particular engine. So that's number 13. So number 15 says, an ice making machine operates in a Carnot cycle. It takes heat from water at 0 degrees Celsius and rejects heat to a room at a temperature of 24 degrees. So 24 degrees to 97 Kelvin. Okay, and suppose there's 85 kilogram of water. Suppose 85 kilogram water at 0 degrees Celsius are converted to 0 degree ice. So from water to ice at 0 degrees Celsius. So the question then is, how many joules per cycle does it reject to the reservoir at 300, sorry, wrong question. So are converted to 0, how much heat is rejected to the room? So that's part A, how much heat is rejected to the room. So that is Q heat, high heat is how much? Well, if you're going to convert 85 kilogram of water from 0 degree water to 0 degrees ice, then you have to get the latent heat for, water, and at 85 kilogram, the latent heat for heat of fusion is 334 joule per gram. And so the change of heat then, in this case MC delta T, well, this is no change, so just heat of fusion times mass. So in this case it would be 85 kilogram or 1000 grams times 334 joules per gram. So we get a total heat that needs to be extracted from water, and that turns out to be, if you calculate multiply these two, you're going to get 2.84 times 10 to the 7th joule. So that is how much heat that will be needed to be taken away from water. So that is in fact the QC, 2.84 times 10 to the 7th joule. Okay, so how much heat is ejected to the room? Well, if you know that it is a Carnot cycle, Carnot cycle has a very special relationship, and that is the TA, or the cool temperature, divided by T hot minus T cool, is same as the ratio of their heat, if you know the temperature. Now, since we do know the temperature, the T cool is really at this temperature, so 273 Kelvin, and the difference in the temperature, in this case 297 minus 273, which is in fact 24, so 24 is equal to QC, which is this number, 2.84 times 10 to the 7th. Then you can figure out what QH is, the high heat. So if you plug in the numbers and you get this number, and then if you just solve for Q heat, high, you end up getting basically 3.09, times 10 to the 7 joule. That is, everything here is known, so all you have to do is solve for QH. Now this is the heat that will be pumped out. So the amount of work done then is simply, in this case, this will include the amount of work plus the heat that is to be removed. That is, work is Q high minus Q cold, which is in fact 3.09 times 10 to the 7 minus coming in was 2. This is in fact the same as Q in or Q cool in this case for refrigerator, 2.84 times 10 to the 7th joule, and the result is if you subtract the 2, you get 3.09 minus Q in 2.84. So we have 2.49 times 10 to the 6th, okay, joules. So there's only 2.49 times 10 to the 6 joules, and that is the work done by the this should be the work done by the machine. Sorry, by the machine to supply to the device. So how much energy must be supplied to the device? So this should be the amount of energy supplied to the device to make the refrigerator pump out this amount of heat. So the total heat expelled will be this one, which is the sum of the work and the heat to be expelled. So that is the total heat. Anyways, so the answer is in fact this is correct. 3.09 times 10 to the 7th. 3.09 times 10 to the 7th, yeah. And this is 2.49 times 10 to the 6th. That's correct. And the amount of heat to be removed is this one. Okay. So number 17. Number 17 says a Carnot device extracts 5,000 joules of heat from a body at negative 10 degrees Celsius. So if it extracts, it sounds like it is going to be a refrigerator. But anyways, so it extracts at a temperature Tc is negative 10 degrees Celsius or 263 Kelvin. Actually, it says how much work is done if the device exhausts heat into the environment at 25. Well, if you're working to remove heat from a low temperature to a high temperature, that's called refrigeration. So part A says if the exhausted heat is at an environment of 25 degrees Celsius, well, that would be higher than the initial temperature at negative 10. So that would be refrigeration. And part B is if the exhaustion to the environment is at 0 degrees Celsius, which is still higher than the initial temperature at negative 10. So this will still be a refrigeration. However, part C, the temperature is negative 25 degrees. Now that is lower than your initial temperature, negative 10 degrees. So this will be an engine. Okay, it will operate like an engine to do work, and then the heat will be expelled to a lower temperature. So in each case, the device is acting as an engine or the refrigerator. So we said that if the output temperature, T out, in this case will be higher at 25 degrees Celsius, and B, so this is refrigeration. And if the T out is 0 degrees Celsius, it's still refrigeration compared to the initial temperature of negative 10. But part C is if the temperature actually is negative 25. Well, if that's negative 25, that means this is actually cooler than the initial one. And in that case, this will consider to be higher. So Tc in this case is negative 25 degrees Celsius plus 273. So in each case, so this will be refrigeration, but this will be an engine. Okay, so now they want to know, well, how much work is done? How much work is done in each case? What we know from before is that the work is done is according to the formula Tc or refrigeration, okay, minus that equals to Qc over work. Okay, so all you have to do, well, work is actually the same as Q high minus Q cold. This is for refrigeration only. So we know that in both these two cases, all you have to do is plug in the initial temperature, which is 263. T high, in this case 25 or plus 273. So 273 will be 298. So 298 minus 263 is equal to QC over the work, right? Now they say that QC, the amount of heat that is extracted is 5,000. So in fact QC is 5,000 joule. So I'm going to put 5,000 in here, and this is the work, okay? You can actually figure out what the heat of high temperature would be, you know, instead of figuring out work. But this is work. So now I can cross multiply and get what W is. So W is basically 5,000 divided by this times that. So 5,000 times bracket 298 minus 263. And then divided by 263. So I get the work of 665 joules. Now here's a question you have to make sure that you know the W is positive or negative. Now this is the amount of work, it's absolute value, but if they say how much work is done if the device exhausts heat to the environment, since this, they say how much work is done. Well, they didn't say how much work is the environment doing to the system. But in this case, it would be the environment doing to the system. But if they didn't say, if they didn't ask what is the work done by the environment to the system, then you have to assume that the W that they're talking about has a plus or minus sign that you have to worry about. If they were to ask what is the amount of work done the environment does to the system, then you can just say 665 joule. But if they didn't say that, like in this question, they simply say, what is the amount of work done? What is the amount of work done in such a case? Well, the amount of work done, if you say 665, it actually, being positive, actually would mean that it is the system doing work to the environment, like in the heat case. But this case is refrigeration. So W will have to be negative 665, meaning, or if you want to be careful on the exam, do write down 665 joules by environment to system. So in that case, then you don't have to worry about plus or minus when you say so. But if you didn't say so, then put a negative sign, then you'll know that the W means the environment doing work to the system with a negative sign. Okay? If you want to put positive sign, then say so by saying by environment to system. Okay, so that's W. And then if what about if the case was 0 degrees Celsius? Well, still refrigeration, so I'm still going to use the same formula, Tc, which is still the cold one. So in this case, it's basically the same as this one, 263. But instead of 298, it will be 273. 273, which is 0 degrees Celsius, right? Minus 263 equals to 5,000 over W. So in this case, the W can still, we just cross multiply 5,000 times 10 divided by 263. I get 190 joule. Again, this is refrigeration, and then the question did not specifically state which way. So they just say how much work is done. So in that case, you have to say negative 190. Or if you don't say negative, then you have to say 190 joules done by the environment to the system. Okay, that's what refrigerators do anyways. Okay, the part C now, though, is different. Part C, that the temperature is actually far lower than what you start out with. This is actually negative 25 degree, not a negative 10 degree. So this will be actually a heat engine. That is, you're going to be putting work to remove, putting heat in, do some work, and get rid of some heat at the end. Okay, so, but therefore you cannot use this formula now. This is formula is only available for refrigeration. But for Carnot engines, the ratio of the cold to heat is in fact the same as the temperature. Okay, that is only for Carnot engines. Okay, the ratio of their heat and the temperature are the same. But in this case, the cooler one, in fact, is the negative 25 degrees Celsius. So it is 273 minus 25. That is the cooler one. The hotter one is in fact what you start out with, 263. Okay, and the heat that is pumped in is no longer considered the cool. It's actually at the bottom. The bottom QH is the amount of heat that you add, or Q in. So this is actually 5,000 at the bottom. This is actually now the heat to be exhausted to the outside world. So by doing this, you can figure out the amount of heat out, which in this case, if you cross multiply, 273 minus 25 times 5,000 divided by 263, I get a QC is 4715 joule. So the amount of work done then is QH minus QC, which is 5,000 minus this guy. So I get the answer of 285 joules. So in this case, a high heat coming in, which is 5,000, will leave some work, 285, and then the rest, which is this, will be exhausted or expelled. So in this example, this will be positive, right? This will be positive because this is in fact the work the system does to the environment. So that will be in fact positive. It looks like the answer are all correct. Okay, so that is number 17. Now let's look at number 19. Number 19 says, show that the efficiency E of a Carnot engine, efficiency E of a Carnot engine and the coefficient of performance K of a Carnot refrigerator. Now this is for refrigerator, coefficient of performance. This is the efficiency of heat engine, Carnot heat engine. They want you to prove that if the heat of the two reservoirs, that's hot and cold heat sources, are the same, okay, except in one case the Carnot is going this way to do work to the environment, the other way is backwards to suck in heat and then expel it as a refrigerator. But anyways, these two, if you have the same heat source cold and the same heat source hot, then these two are related by the equation K is same as 1 minus E all over E. Okay, they want you to prove that. Well, the best way to do this would be to write down the definition of each. What is the efficiency for heat engine? They assume that there is a heat source of cold. There's hot and cold. Okay, for example, for the heat, there's a hot to cold and doing some work. For refrigeration, is removing the heat cold and add some work to expel it at heat high. Anyways, so let's find out what E is in terms of engine. Carnot heat engine says the efficiency of all that is amount of heat going in divided into the amount of work that gets done. Okay, that's typical engine efficiency. But for coefficient of performance for refrigeration, then it is the amount of heat that you are removing divided by the amount of work that you have to do to remove the heat. Now we got to be careful here because in this case it is the heat. Okay, that is this heat is actually the high heat. Okay, that is QH, a higher of 2. And work in this case is high minus low over this. Okay, we know that. But in the case of K, the coefficient of performance for refrigeration, the in is actually the low heat, the colder one, and divided by the work. But the work in this case is the eventual high heat minus the initial cold heat. Okay, that is the difference between the two to get the work done. Okay, so we know these two. So if you look at K, this one, and this part appears to be the same, right? So what we can do is, if you divide the bottom here by QH, you're going to turn the bottom into E, like what they are expecting here. So I'm going to keep the K to mean QC all over QH minus QC, but I'm going to now divide top and bottom by QH. When I do so, the top is QC over QH, but the bottom is exactly what the definition of E is, okay, right here. So I'm just going to write E. Further, you see here, this part is almost like this part. So if I just split this into two fractions, QH over QH minus QC over QH, and that's E. This is 1. So E equal to 1 minus QC over QH, which means I can move this guy over, move the E over. QC over QH is therefore 1 minus E. So the top here, I can now replace the top by 1 minus E. Therefore, it's 1 minus E over E. That's exactly what K is, and therefore the end of the proof. Okay. So that is the way you prove it. The engine and refrigerator operate between the same hot and cold reservoirs. What is the K for the limiting values? E approaches 1. So if you take a limit, what's the K if E is approaching 1 of this expression? Well, if you approach 1, this will be 1 minus 1 over 1, which is perfectly 0 over 1, which is 0. Okay, so K is approaching 0 if E is approaching 1. So if E is approaching 1, then K will be approaching 0. On the other hand, if E is approaching 0, as what part B says, and what is K approaching? So if E is approaching 0, well, then basically you have 1 over 0, okay? 1 over 0, and then the answer is undefined, or infinity. So that is, if E is approaching 0, then K approaches infinity. And that is the correct answer. Okay, so that's it.